So welcome back, everybody. I'm Nikhil Srivastava. I'm a senior scientist here at the Institute, and it's my pleasure to introduce this session of talks by our research fellows. So research fellows are early career researchers, so postdocs or faculty members who spend a semester at the Institute in one of the thematic programs, and each program usually has 7 or 8 fellows. And they're really responsible for a disproportionate amount of the scientific and social activity of the program. So many of the best discoveries are made by them, but they also organize the music nights, the board game nights, and so on. And many of them go on to leading positions in academia and industry, and many of them are also supported through our industrial partnerships. And so we have 5 talks. Our first speaker is Hanna, who's in the Algorithmic Foundations program, and she's a Google research fellow.
Right. You can hear me? Good? All right. Thanks, everyone, for coming back for lunch to hear my talk. My name is Hanna. I'm a research fellow here in the Algorithmic Foundations program. And my work is primarily on a theory of data structures. So today I'm going to tell you about a class of data structures that I think leads to a lot of really interesting problems called history independence. So first, kind of like a high-level intro of what we're doing here. One of the things that distinguishes data structures from more general algorithms is that they must constantly maintain some internal memory state and be able to answer queries at any time in response to an online sequence of operations. So if we examine this memory state of the data structure, there's a lot of things that we may be able to learn. For instance, operations in the history that relate to elements that are currently there, such as the fact that they were inserted. That one is pretty natural. But there's many other types of things that are less intuitive that we might be able to learn by looking at the memory state. So operations that relate to elements that were in the data structure previously but have since been deleted, the order in which those operations came in, or some of the choices that the algorithm made in implementing the data structure. And kind of the point of history independence is to say that while we may not be able to help revealing information of the first category by looking at the data structure's memory, the data structure does have a lot of flexibility in what it reveals about these other 3 categories. Okay, so first a kind of informal definition of history independence. In a history independent data structure, we distinguish between the memory layout of the data structure and its logical state, and the memory layout at any time only depends on the current contents of the data structure at that time. So there's a little bit of an asterisk on only here. It can depend on other things such as the internal randomness of the data structure. But the key thing is to say that the memory state is not a function of the history of operations. Therefore, by looking at this memory, we don't learn anything about the history. So this has found a lot of uses as a security guarantee. So the guarantee it gives you is that if you had some malicious actor that was able, unfortunately, in some breach, to gain access even to the internals of your data structure, in that case, you can't help that they learn about the data that's already there. But history independence gives you an information theoretic guarantee that you don't leak any additional information. So as I said, this has naturally found a lot of applications in privacy, in securing things like voting systems, file systems, and databases, and so on. My work has typically focused on these latter categories, which is looking at the theoretical side of providing history-independent versions of traditional data structures, such as dictionaries. Okay, so before I run through an example, I'm first going to give you an equivalent and slightly more formal definition that's easier to work with. So there's a few different variants of history independence. For the strongest one, under some light conditions, Hartline et al. Prove that it's equivalent to saying that your data structure has the property of unique representability. So I can have some randomness, but if I fix my random coins, then for any set of contents at any time, the data structure has one canonical representation that the memory can be in. So let's look at an example. Kind of one of the most widely used data structures is a hash table. And a lot of the classical implementations do reveal quite a lot about the history of operations that happened. So typically the way you would resolve collisions in a hash table, either with chaining or linear probing, is that you put elements in the slot that they want to hash to if it's open. But then say another insert came in, say X here wants to go to the same slot as Y. Now, if I was implementing with linear probing, I would look for the next empty slot and put X there, and so on. This could happen a few times. Now Z says that W has to move over. So essentially what's happening here is that if I look at the layout of my hash table, I'm actually kind of just giving you a log of the order in which these inserts came in. So this is not great from a history independence perspective. But it's actually not too difficult to make this strongly history independent. All I have to do is say that rather than using the order of operations to decide the order my elements go in, I have to pick a canonical ordering that depends only on their keys, so not on time. So for example, I could hash the keys again to some random priorities. Here, I just used alphabetical ordering by hash. So this is kind of an example of how it's typically not very difficult to think about how to make data structures like this history independent or to put them in a canonical representation. A lot of the complexity comes from showing that I haven't made my data structure much less efficient. Because as in this example here, if element X came in after all these, I would have to move everyone down in order to enforce this ordering. So typically, this is where randomization comes in handy, and you prove that in expectation or with high probability, your data structure satisfies similar bounds to the non-history independent versions. OK, so I'm going to quickly touch on some of the types of problems that I'm interested in with history independence. They broadly belong to two categories. So one is whether we can make history-independent versions of traditional data structures that are efficient and that also marry history independence with some practical real-world models of computation. So first, I've looked at the external memory model, which is widely used both in theory and in practice. But traditionally, it's been difficult to have history-independent versions of external memory data structures because external memory data structures use amortization in order to have efficient implementations. And there's some inherent tension there between amortizing or batching up your operations and not revealing anything about the history. So myself and my co-authors have a paper at our recent pods where we kind of resolve this tension with efficient and more natural constructions of classical external memory data structures, such as B-trees and making an external memory skip list. And then more recently, this is a project I'm excited about because I started this up at Simons with some other long-term participants that I met here. This is looking at history independence in the asynchronous shared memory model. So if we have concurrent data structures with many threads operating at once, there's a few challenges here. One is even just formally defining what we mean by history independence in this setting, but also the way that these threads would typically enforce correctness in a concurrent data structure is often by using a lot of identifying information that would leave around a lot of the history. So there's a lot of interesting questions there that we're still looking at. All right. The second kind of problem that I'm also very interested in is whether history independence can be used not from a security perspective, but to make traditional data structures be even faster. So there's a few natural examples that have come up in the past few years. All of these also happen to involve at least one long-term participant at this workshop, where in the effort to create a better worst-case algorithm for a problem against an oblivious adversary, a history-independent algorithm has naturally fallen out. This happened in Cliff's paper with maximal independent set, as well as at a recent paper for maximal matching. And I also have some work where a history-independent algorithm broke through progress on a long-standing open problem in list labeling, which is essentially a primitive where we maintain elements in sorted order dynamically. So something that I'm interested at in the future is whether there are other algorithmic problems where history independence can be used in this way. So since it keeps popping up naturally, maybe history independence has natural properties that help us defeat oblivious adversaries to make faster algorithms, or maybe we can classify the types of problems where that's the case. I'm also interested in looking at generalized or more approximate notions of history independence because it can be a strong property that's a little bit too strong to maintain practically, but there hasn't been a ton of study on loosening it up. And I would also be very happy to chat with any practitioners who see usefulness in history independence or canonical representation data structures more generally. All right, thank you very much.
Questions? Yeah.
Are there any deterministic history independent data?
Yeah, good question. So yes, you can certainly construct deterministic history independent data structures as long as your deterministic layout is not history dependent.
Any non-trivial examples?
Yeah, so I was going to say the problem with that is that they tend to be less efficient because the randomness is really useful for guaranteeing that you're kind of not doing too much work on average. Off the top of my head, I don't know of a non-trivial example, but I'll think about it and get back to you. Yeah, thanks.
Any other questions? Okay, well, thanks again.
Okay.
Yeah, you can put that in your pocket.
Okay.
Our next speaker is Halikias from the Complexity and Linear Algebra program. Please.
Okay, hi. So I'm going to be talking about the problem of matrix recovery and operator learning, specifically in the context of small amounts of data. And this work is joint with Nicolas Boulet, Sam Otto, and Alex Townsend, who are at Imperial College London and Cornell. The broad problem of operator learning is to learn properties of a dynamical system or a PDE just from data. So there's tons of areas where this comes up. This picture is from GraphCast, which is a DeepMind model that does operator learning for weather forecasting and has seen some pretty exciting, unprecedented results. But really, this problem arises anytime you have a physical system that you can query for data, either using physical experiments or simulations, and sort of applies to, for example, turbulence modeling, fluid flows, plasma dynamics, tons more. And the key tool in operator learning is the neural operator, which was developed as a generalization of a neural network to map between infinite dimensional spaces. So you can imagine in the context of PDEs, you'd like to map between Sobolev spaces. And neural operators can serve as reduced ordered models that can speed up existing numerical solvers. So this is particularly useful in contexts where you have a complex system that's hard to simulate using traditional methods. For example, turbulent flow that requires a very fine discretization or high-dimensional PDEs. So your reduced order model will be less accurate, but it will be much cheaper to evaluate and apply. So this is especially useful in contexts where you need to apply an operator many times. It can also be used to solve inverse problems, and in cases when the underlying PDE is truly unknown, to discover unknown physical laws. So the benefits of these methods are that they're completely data-driven. They're also discretization independent and potentially much cheaper and faster.
Should we think of this neural operator as like a time evolution, a time-stepping operator?
You can, but I guess I'll describe it more exactly on this slide. So I want you to think of it as a solution operator of a PDE. So here we have a PDE. LU equals F, L is a partial differential operator, U is a solution, and F is a forcing term over some domain omega. And traditionally, when we solve a PDE, we're of course given L and F, and maybe some information like boundary conditions or initial conditions, and we want to find the solution U. But in PDE learning, we ask a slightly different question. So instead, we're given data pairs of forcing terms and solutions, and we want to learn the solution operator, which maps each fi to the corresponding ui, or at least approximate this solution operator. So deep learning techniques have achieved some success in practice on these problems. You might have heard of deep O-nets or Fourier neural operator, to name a couple. But this problem is very poorly understood from the theoretical perspective. And a crucial issue here is that, unlike in some other applications of deep learning, data generation can be prohibitively expensive. So my research is really about understanding the theoretical underpinnings of how operator neural networks work. And in particular, I'm interested in these questions. So what does the best training data look like? And of course, how much do we need? And we've developed a framework for answering a lot of these questions with theoretical guarantees. And we use ideas from randomized linear algebra, PDE theory, compressed sensing, theoretical computer science, and a lot more. So I guess I want to emphasize that this is like a really exciting, emerging area of scientific machine learning, and there's a lot of interesting work to be done. In this talk, I'll just give an overview of a couple main results, and I probably won't have time, but maybe some open questions. So the key connection to a linear algebra problem is that we're going to consider the problem I presented in the last slide for linear PDEs, and we're going to recover the solution operator L inverse in this particular integral operator form. So L inverse takes in a forcing function f and integrates it against some Green's function kernel g over the domain omega. And with this representation, G uniquely defines L inverse. So we can rephrase our operator learning problem as using as few of these pairs as possible to find a G that satisfies this integral. And if you look at this integral, you can imagine the easier version of this problem is if it's a discrete problem. So your integral becomes a sum, your functions become vectors, and G, this Green's function kernel, is just a matrix. And we get this analogous, and I want to emphasize it's analogous, not equivalent, but an analogous problem in linear algebra, which is that you have an unknown matrix A that you can query with matrix vector products. So you can construct an input X, view the output A times X, and similarly with A transpose. And the goal is to recover A using as few of these queries as possible. So this is sort of a nice toy problem and a good way of thinking about operator learning. And this might look familiar because this is a really common, I guess increasingly popular common in numerical linear algebra, where we can speed up a bunch of linear algebra routines by multiplying our matrix of interest by random vectors. And so this is a really important connection between these areas. So of course, if A is an n by n matrix, we can always multiply by the n basis vectors, the classic basis vectors, and recover A column by column. But if n is very large, this is very inefficient. So ideally, if we know in advance that A is structured, for example, if it comes from a PDE, we'd like to recover it using far fewer queries. So this brings up the problem of structured matrix approximation. So we can assume slightly more generally that A is close to some structured matrix. And our setup is that we have matvec access again to A and its transpose, a structured class S, which we can think of as diagonal matrices or low rank matrices, and a tolerance epsilon. And the goal is to find a near optimal approximation B tilde in the class S, where near optimal just means that the error in the Frobenius norm of your approximation is at most 1 plus epsilon times the best possible error from any matrix in S. And this setup, though I motivated it from operator learning, is generally, this is a question of broad interest, both in numerical linear algebra and theoretical computer science. And I don't have time to talk about it today, but I'm doing a lot of work with Chris Musco, who's at NYU, and his group on this problem. So this should also look familiar to you, possibly if you have been following randomized linear algebra, because there's some classes where this problem is really well studied. So the classic example is the problem of low rank approximation, so getting the best low rank approximation to a given matrix. And the randomized SVD is one of these great algorithms that computes a near optimal rank K approximation using only on the order of K over epsilon queries with A and its transpose. So the first main result I'm going to talk about is this result that is called elliptic PDE learning is data efficient. So we're going to restrict ourselves to a particular class of PDEs that are nicely behaved, which are elliptic PDEs. And in practice, we observe that it's easy to learn these types of PDEs using relatively small amounts of data. So this is what's been coined as the data efficient phenomenon. So in this plot, I'm just comparing 3 different neural operator architectures that all reach the same discretization plateau, but require relatively small amounts of data to get to that plateau. And so,
What's the discretization plateau?
so your model can't expect to do better on this problem than this plateau because of the discretization of your functions that came in. Yeah, but the story here is that is really like the first regime of these plots approaching this plateau. And so this was observed in practice, but we provided a theoretical justification for this behavior by showing a fact that's actually not necessarily about these particular models, but a stronger fact that this problem of elliptic PD learning is intrinsically data efficient. So this problem intrinsically requires small amounts of data. So this is our theorem statement, and I unfortunately can't describe to you the algorithm or the proof, but we show that there exists a randomized algorithm that gives you an approximation to your Green's function with only log to the 5th 1/epsilon operator function products. And this is a randomized algorithm, so we show that it succeeds with high probability. And the main tools, just a sketch of what went into this result. Again, we're using ideas from a lot of different things. So first we look at the PDE theory for elliptic PDEs, which tells us that the Green's functions of this class of PDEs look like a class of matrices called hierarchical matrices. So this is a picture of what those look like. Basically, these are called hierarchical low-rank matrices, and they're very well studied in numerical linear algebra. They're not globally low rank, but they can be subdivided into these green blocks of sort of recursive sizes that are themselves low rank. And so what we did is we looked at, we did an analysis of hierarchical matrix approximation algorithms in the discrete setting, and then also transported these ideas to infinite dimensions, both the algorithm and the theory.
So what is it about ellipticity, which
Yeah.
is the continuous analog of this?
Yeah, so I guess you can think of low rankness as an analog of smoothness. And the elliptic condition you have on your PDE, there results about, so if you look at your hierarchical matrix, its off-diagonal blocks are low rank, and off-diagonal blocks represent long-range interactions in your domain. So I guess the basic example is the heat equation is commonly used for this. But yeah, you can actually prove like very rigorous, wow, 3 minutes went by so fast. Okay, you can prove very rigorous estimates on the low rankness or the singular value decay of these blocks based on the smoothness of your equation. Okay, so the second main result is resolving something that was called the adjoint mystery in operator learning. So just recall that the adjoint is of an operator A between 2 Hilbert spaces. It is given by this symmetric inner product property in the Hilbert spaces, but you don't have to think much about that at all because in finite dimensions, this is just the transpose. So you can think about this just as the transpose. And so previous theoretical guarantees for operator learning all rely on access to both the PDE, or the partial differential operator, and its adjoint. But this is actually very unrealistic because the adjoint corresponds to a different equation, which you can't realistically sample for data. So this is sort of a gap between theory and practice because on one hand, our theoretical guarantees all assume you have a particular type of data, but in practice, we see good performance without this type of data. And another classic example is low-rank approximation, which intuitively requires access to both A and its transpose because you need to recover both the left and right singular subspaces or top singular subspaces of the matrix. So our contribution was proving the first adjoint-free guarantees for these types of problems. So first in the low-rank approximation setting, for matrices, we sort of quantify the dependence on access to A transpose. And then more generally, we introduce a method for adjoint-free operator learning, which is using ideas from preconditioning in linear algebra. So you pick a prior self-adjoint operator L and use it to learn your operator to high accuracy. So I'm not going to dwell on this too much because there's a lot here, but the basic idea is that this is for elliptic PDEs, you can choose your preconditioner to be the Laplace-Beltrami operator and assume some elliptic regularity in terms of this factor k. And if you do n samples, so n queries, your convergence to the true operator is like 1 over n over k to the d. And so I guess one thing to emphasize as a summary, and I've shown you 2 results. The first is exponential convergence for operator learning methods that use both an operator and its adjoint. And I just showed you, we also get algebraic convergence when you only use one side. And there's a ton of interesting open directions for this work. So I'm thinking about learning harder PDEs, which correspond to more complicated classes of matrices that still have low rank structure, but it's much harder to identify. There's also ideas from theoretical computer science and property testing, and also potentially information theoretic lower bounds for these problems that are of great interest. And finally, nonlinear PD learning is wide open, both in terms of theory and practice. So yeah, that's all I had to share to you today, and these are some of the papers you can read about my work. Thank you.
Any questions? I have a question. So in this area, you have to go from this continuous PDE to a discrete one. Is the type of discretization you use, is that a subtle thing? Or?
No, so all these, the two main results I presented are actually in the continuous setting.
I see.
So that's something we really try to avoid, actually, is to have discretization-dependent results. But yeah, so there exists like analogs of the randomized SVD for Hilbert-Schmidt operators.
Okay, well, this is a finite dimensional object, but it's fine, it makes sense.
Oh yeah, in this case, it's finite dimensional. Yeah, sorry.
But you don't use
This
that.
is a finite dimensional object defined over like defined over like the unit square or something.
Okay, got it.
Yeah.
Any other questions, comments? Okay, well, thanks again. Okay, so next we have Naama and David, who's a Google Research Fellow in the algorithmic notations for please.
All right, thank you. So yeah, my name is Naama Ben David. I'm an assistant professor at the Technion, and I'm here this semester as a Google Fellow at the Simons Institute. I'm going to be telling you about our work on Byzantine agreement with predictions. This work is joint with Ayaz and Seth from NUS and Faith from Toronto. So I'll start by just very briefly talking about what Byzantine agreement is. So in an agreement problem, we have many processes in a distributed system, and we want them all to agree on a common input. And this is a really useful primitive in a lot of different applications. So blockchains make use of agreement to agree on a common ledger of transactions. Distributed data structures will also use consensus in order to build consistent data structures. And it's also used in replication to withstand failures in a distributed system. Now, that's about agreement. Byzantine agreement means that we want to solve agreement in the presence of some malicious processes. So some of our distributed system has been sort of taken over by malicious agents, and they're trying to make our protocol fail, and we need to solve agreement among the correct processes. And usually the way that we do this is we don't try to detect who is Byzantine. We kind of assume that the Byzantine agents are smart enough to hide themselves. So we don't attempt to detect them, we just try to handle attacks if they occur, right? So we don't know who is attacking, but we're kind of saying, okay, well, we can give ourselves the guarantee that even if there are attacks, we will solve consensus. But the question in this work is, well, what if we could detect something about malicious behavior, right? What if we had some information about who might be the malicious attackers? Could we use that information to our advantage? So in this work, we have this concept of, we have some predictions. So we can think of them as some security tool that gives us predictions on who might become Byzantine or malicious in our system, right? So if we have a distributed system, what we assume is that each machine in our system is equipped with this tool or oracle that gives us predictions on who else in the system is malicious. Okay. And this tool could be implemented in practice in all sorts of ways. So there are some papers that talk about creating such tools, but in general, you could analyze network patterns or look at sort of irregular messages that are being sent, or if you have some information about, say, hardware that is easier to attack on some of the machines, or if you have some information on maybe the location of the machines that are more likely to be attacked, you might be able to sort of fold that into a predictor. We kind of black box that as we have some oracle that gives us predictions on who is faulty. Right, so each machine has this oracle, and it might tell a process in our system, well, I think, the other two processes are going to be faulty and the rest will be correct. And someone else might get differing predictions, right? They might overlap a little bit, but they might differ. They might be wrong. And so now the question is, well, can we use such information to help us solve agreement, right? And even if that information is wrong. And the answer in our paper is yes, this can be used, even if the predictions could be wrong. In cases where they are correct or they're not absolutely horribly wrong, we can use this to speed up agreement algorithms. And in particular, in our paper, we show that you can speed up, you can decrease round complexity. Okay, so just like a very quick sort of slightly more detailed description of what the problem is, and then I'll be able to state the results, and then that's basically all the time I have. So in consensus or agreement problems, we have many processes, they all receive some input, and they want to agree on one of those inputs as the output, right? So let's say in this example, it's all binary inputs, everyone receives some input, either 0 or 1. We want them to be able to output the same at the end of the day. Right, so they communicate and somehow they decide on a common output. And it should be one of the inputs, right? They can't just ignore the inputs and a priori just decide I'll always output 1. So if all of them have input 0, then all of them must output 0 as well. That's basically all the requirements. And we might have some malicious or Byzantine processes that we don't require anything on them for outputting anything or outputting the correct thing, but we want anyone who isn't malicious to all agree. Okay. And then in our paper, we define these predictions. And the way we define them in this paper is that we assume that each process receives this sort of string that has 1 bit per process in the system that just tells it, is this process malicious or not? Okay, so they get these strings. I think I have examples on this slide. So let's say P1 got this prediction string that tells us, well, everyone will be correct except for P3. So in this case, P1's prediction is correct. And you can notice that everyone else has wrong predictions, or predictions that are wrong about at least someone. Okay, and so this is sort of a typical example that we want to think about. The predictions might be kind of accurate, right? Most people realize that like P5 is going to be correct, but they were wrong about who is going to be the malicious party. Okay, and we also in the paper talk about a metric of how good was the prediction in this current execution. So we just count the number of bits across the system that were wrong, right? So across the system, we have n squared bits, right? So n bits per process, and we have n processes. And we just count the number of bits that were wrong. So in this example, let's say this prediction predicted that P2 will be faulty, but actually P2 is correct. It predicted that P3 will be correct, but it's actually faulty. And so we just count the bits that are sort of flipped, yeah.
Doesn't P3 get to vote too?
Good question. I mean, it doesn't. So because Byzantine processes can do whatever they want, they can also lie about what their predictions were. So in our accounting, we kind of don't look at what the predictions were that they received. Okay. Yeah, good question. All right, so in this example, we have 8 wrong bits, right, across all of the predictions that we were given. Okay, and with this setting, right, what we said is our results are that we actually can use such inaccurate predictions to still speed up Byzantine agreement. And we actually show that you can improve round complexity. So our theorem is that there is a Byzantine agreement algorithm, and we look at it in the synchronous setting, so we know exactly how long messages take in order to arrive at their destination. There is a Byzantine agreement algorithms that uses predictions that tolerates T failures when T is less than a third of the system, which is optimal in normal Byzantine fault tolerance, and terminates in this many rounds. So it's basically the minimum between f+1, which is the optimal round complexity without predictions, and b over n, basically, where b is the number of faulty bits, right? So basically, the better the prediction is, the faster we will be. So this is the result. It is asymptotically, so our algorithm does add some constants over what is optimal without predictions. If the predictions were really terrible, our algorithm will be a little bit slower than an algorithm that didn't try to use predictions, but only in constants. So that is the main result. I'll give you sort of a one-slide, very, very high-level idea of how we achieve this result. The idea is as follows. In an ideal world, everyone would get correct predictions, and those predictions will all be the same, right? So everyone, let's say, correctly predicted that P1 will be Byzantine and everyone else will be correct. In that case, what they're going to do is they're just going to look at their prediction, and they're going to say, well, okay, we can't listen to P1 because that one's faulty, but let's all listen to the lowest ID process that isn't faulty. Okay, so they all choose P2 as sort of their leader, and P2 just sends its input to everyone, and everyone listens to them and will not listen to anyone else, and in particular will not listen to a faulty process. And so everyone just receives the right, the value they should choose, everyone agrees, and we're done in one round, right? So this is sort of ideal scenario. Unfortunately, that's not our real scenario. So there's two problems. One is that predictions might be wrong, and the other is that predictions might be different on different processes, right? And so in our paper, we kind of showed that we can get around these problems. We basically make use of an algorithm that can already handle Byzantine leaders, so it's not the end of the world if you end up choosing a leader that is Byzantine. Basically, you will recognize that, oh, it didn't go well, and you'll move on to the next round and choose another leader. And the problem is that if you just go by your prediction and you go sort of one by one, you might be choosing different leaders in each round, and you still wouldn't sort of converge on everyone listening to the same leader at the same time. And so we basically show how to choose leaders carefully by communicating on what each person's predictions were in order to ensure that eventually everyone chooses the same leader that is correct, and then we can terminate. And again, the better the prediction quality was, the faster this will happen. Okay, so that's basically all I wanted to show you. I'll just summarize, and then I'll be happy to take questions if we have time. Right, so we basically show that if we have predictions on who is faulty in a Byzantine distributed network, we can speed up agreement. Okay, and there are many future directions that kind of stemmed from this. First is to consider different types of predictions. Doesn't necessarily have to be sort of 1 bit per process telling us like who is faulty. You could imagine predictions that give us sort of some confidence on like how confident I am that this person will be faulty or not. You can imagine predictions that that have some guarantee of quality, right? So we assume that there is no guarantee of quality, but if you could tell me that my predictions are always at least 80% correct, could I do something stronger? You could also imagine predictions not on faultiness, but on like timing of messages or what the inputs will be or something like that. We also haven't looked into that. In general, I will say that this sort of view of predictions on faultiness leads into a lot of related work on, well, can we move away from the conventional failure assumptions that Giuliano also talked about in his talk earlier before lunch. Basically, usually we assume that everyone trusts parties equally, and we just have a threshold of as long as there will be less than 1/3 of the system that is faulty, we can solve agreement. You could imagine all sorts of different failure assumptions, like, well, I know that failures will be correlated, so can I, knowing that if one person failed, it's likely that others in their area will fail, could I do something different or stronger? There are a lot of different sort of different failure assumptions that we could apply, and I think this kind of falls into that category. And finally, predictions have been used a lot in sort of online algorithms, but very little in distributed systems. And I think there's a lot to be studied in how we can use such predictions, not necessarily even in Byzantine agreement, but even we could use it for shared memory algorithms, for predicting scheduling and all sorts of things like that. So I think a lot of distributed systems problems could benefit from such predictions. And so I'll leave it at that, and I'll be happy to answer questions.
Any questions? Yes.
What about dynamic failures? Standard Byzantine literature deals with the process that failing can change over time as long as under n/3.
Right, good question. So in this work, we didn't consider dynamic failures, but it could definitely happen. And then even if your predictions don't change, it could be that the quality of predictions change over time. I think our algorithm would be able to handle that, but I think if you sort of explicitly take that into account when designing the algorithm, you could probably do better. Yeah.
One more?
So I imagine that your result generalizes like immediately to the case where you don't have a fully connected network, and the number of Byzantine faults would probably lower, but the same ideas would apply, right?
Yes, I think so. I think just like sort of classic fully connected Byzantine agreement results generalize, I think this would generalize in the same way.
Do you think you can think of a model where, by having this extra information, could actually increase the number of faulty processors rather than just the rounds?
Yes, we actually discussed this when we were doing this work. It seems like there's a very natural, that's a very natural question, right? If you take this to the extreme, right, and your predictions are always perfect, and you know who the Byzantine processes are, then you can tolerate arbitrarily many of them, right? Because you just know who they are, you can ignore them, and then it's almost like you don't have any failures. So generally, yes, I think there should be something to be done in that direction. We just haven't sort of figured that out yet.
And finally, just a very short question. You said that 1/3 is optimal, but the no-go result does not take into consideration this additional information.
That's true. So the 1/3 is optimal for no predictions, and in this work we didn't try to improve that. But I can't claim that it's optimal for this setting.
Okay.
Yeah.
Thank you.
Yeah.
Thank you. Okay, and now we have Tegan also from the Algorithmic Foundation program. Do it.
Okay. Yeah, I'm Tegan Wilson. I'm currently a postdoc at Northeastern, and yeah, I'm a research fellow here with the Algorithmic Foundations program. This talk for me is going to be a pretty high-level talk just of the overall research area that I like and have been working a lot on, to tell you the problem space, tell you some of the motivations behind it, and a little bit about some of the results I'm excited about. Very, very broadly, the problem space is on routing on networks, specifically for data centers. A data center, if you have one, it's a giant building. You want it to act like one supercomputer, but it's not a supercomputer. It's a bunch of servers, and they need to be connected in some kind of way. And you need to have some routing protocol that says, if one wants to talk to another, how is that message going to go through this set of connections? So this problem space is really like both you have to design a routing protocol, but you also, I mean, if you own the data center, and this is only looking at routing between servers within a data center, you also get to decide what these links look like. And so it's also a network design problem. And these links, what you can do with them, what they can look like, they depend a lot on whatever current network technology you're using to implement them and to implement the network. The network technology that I am really motivated by and that I've been spending a lot of time thinking about are circuit switches, which allow you to change the circuits that are directly connecting nodes. And more specifically, they are these rapidly reconfiguring optical circuit switches that have been very recently kind of exploding in popularity in the networking community. So first, I'm going to tell you about what the theoretical model is for what you can do with these rapidly reconfiguring circuit switches, and then I'll talk to you a bit about like why people are interested in implementing them in data centers. So first, what can you do with them? What can you do if you can change the circuits that are directly connecting your servers? Well, if you have nodes servers, you could decide you want to connect them in this way at some time, and you could decide to reconfigure or change these edges to look in this other way at another time, say time 2, if you're discretizing time into time steps. And then you could further change them. You could reverse this set of directed edges. You could change them again, et cetera. And this is the power that you have, is you can really adjust to the network to what you would like it to be. Reconfigurable network, yes. So why reconfigurable network? Why do we care about these things? Why specifically optical circuit switch? First, compared to packet switches, which is the main switching technology that's implemented in data centers today, in an optical circuit switch, the optical here is doing a lot of work. Messages can travel through this switch entirely as an optical signal. There is no need for you to transfer between optical and electric signals at the switch, which does have some energy and some latency benefits traveling through the entire link. Also, because of this fact, it means that the switch itself is somewhat bandwidth agnostic. If you later develop better technology to read and write light signals at the two endpoints, you don't need to change the switch out to be able to handle that higher bandwidth link. It will just still go through as the light signal that it always was. Also, again, energy saving, but also there's some evidence that there might be cost scaling benefits as well. I don't have the exact citations on this. And then finally, if you can change these edges, it allows your network to potentially specialize to the workload that you're considering. For example, AI training is one of the big areas where people are considering trying to use these kinds of circuit switches, because in AI training, it's very specific, special, regular workloads that you know in advance. So these are all the benefits. And then there are some questions that we still need to ask about, well, how good are the optical circuit switches of today? So reconfigurable network questions, or circuit switch questions here. How fast can you reconfigure these networks? What is the technology like right now? What are people expecting it to become? How many different configurations can you go between? Is it truly that any matching of input ports to output ports can be done, or are there some limitations in how many different configurations your circuit switch can rotate between at any point? And how many nodes can you put on a single switch? There are quite a few different prototype technologies from Microsoft, from Google, from academic labs doing RotorNet. Google's is even, they have some deployed in their data center now. And if you take the best of each of these worlds, then you can get something like nanosecond scale reconfiguration times. You can get all of the different input-output matchings for a number of configurations, and you can get pretty large networks onto these switches. However, in practice, there are trade-offs between some of these different values. People are anticipating that we'll be able to get all of these. But right now, the technology is like, oh, if you want nanosecond switching, then perhaps the number of nodes is less. In our work, let's see. We focused on if you can reconfigure truly this fast, then here's an idea, reconfigure your network all of the time. You don't pay a very large cost to reconfigure. And if you reconfigure more often, you can simulate a much larger degree graph than you otherwise could with just static networks. And so what can you do if you reconfigure your network all of the time and then try to route messages on that? So for example, if we take the same example from before and we have these nodes A through E, and you have some packet starting at A and it wants to send to D, if you are rotating through all of those 4 connections from before, one way that you could get this routed to D is you could wait until you're directly connected to D and then send your packet along that edge. Or alternatively, you could send the packet along this first physical edge that appears. You could let this network reconfigure again, and then B would be directly connected to D, and you could get your packet there even faster, but using slightly more network bandwidth to route. Yes?
Does the schedule have to be on a cycle?
We look at periodic connection schedules, yes. If you can also think about adaptive schedules in which it's not periodic, but you're having some algorithm to decide exactly what it's going to look like. In my work, they're all periodic in some kind of way. Yeah. OK. The packet got to D. I'm trying to remember what my next slide is. C, late. So at this point, I've given you the model. Now we need to ask, well, what things do we care about when we're trying to design networks and when we're trying to design routing protocols? And the biggest 2 things that we would like to optimize for are both the latency of the routing paths that we take and the congestion in our network, or inversely, the throughput that we can achieve with our network. These 2 turn out to be fundamentally at odds with one another. If you want to optimize for one, you'll end up suffering for another. And so in my work, we really try to consider the full Pareto optimal trade-off curve between these 2 values. We've looked at fully oblivious designs, where you need to decide on that periodic connection schedule and the routing protocol before you know what traffic you're going to need to route. The way that works for the routing protocol is you just commit to saying, if I get flow between these 2 nodes, then I'm going to use this distribution to route it. And then you stick to that. And it turns out even in that limited setting with adversarially generated traffic, you can still get some pretty good guarantees. We've also looked at trying to do randomized connection schedules where you randomly choose like n log n connections and then periodically rotate through that. What can you do in that kind of space with high probability? Also, are there more structured random designs that allow you to do well most of the time? We've looked at something that we call semi-oblivious designs, where you're allowed to make some adaptive decisions in regards to the routing, but the connection schedule is still designed before you know what your traffic looks like. And I've been collaborating with network researchers who really care about trying to build simulations and implementations of these designs, in particular the fully oblivious ones. Of all of these threads, I think the only one I'm willing to put a check mark next to is fully oblivious designs, and everything else, there's still pieces of it that are left open at this point. And so that's like oblivious routing on reconfigurable networks. If we take the oblivious out of here, we can get to one of the things I teased earlier, which is if you adapt the routing or adapt the connections, and what that allows you to do, especially, for example, with ML training workloads. I've also done some work on this in the static network model, trying to look at training workloads, comparing different static networks. But I think there's a lot to do with the reconfigurable network model too, and that's less explored at the moment. I think, yeah, that's all that I have for you right now, but I'm happy to answer questions, and this is my email if you want to contact me. Thank you. Yes?
Just a question on the optical circuits. Are you assuming that your devices are passive optic or actually active optical devices? Because configuration cannot be done in both cases. Are you taking that into consideration as you model these topologies?
So in our model, we abstract the costs of that away. Like, for example, Google's MEMS switches, they have mirrors that they actuate, that they rotate to match up input ports to output ports. Microsoft's Project Sirius, it's entirely, they have a laser that tunes what wavelength your signal goes out on, and then they send it through a diffraction grating to do the like matching up. But I guess we haven't taken that into account directly with the theoretical model.
Yeah. You mentioned these are already like implemented, like Google and Microsoft. Like what kind of work do they use?
Microsoft has a prototype design that is not very large in terms of number of nodes, but it does exist. Google has actually implemented these optical circuit switches that reconfigure not at nanoseconds, but at like microsecond level scale. And they're deployed in their data centers. They're using them like to help with their data center network that they already have. So they're not replacing it. They're just like adding on to it to say there's also this reconfigurable component that then they can try to tune to fit whatever their network is. The last paper I saw, they said they were reconfiguring that portion like once a day, but they also published things like 2 years after they started doing them, and that paper's 2 years old, so.
Yeah, once a day and nanoseconds.
Yeah.
Thank you.
Yep.
Okay, so now Robert Andrews from the Complexity and Linear Algebra program is going to tell us something new about the Euclidean algorithm. It's not a small feat.
Thanks, Nikhil. Yeah, thanks for the introduction, and thanks everyone for sticking around. So I want to tell you a little bit of a story. I want to tell you about my research area and some of the problems I work on, and I want to do this just by telling you about the Euclidean algorithm and saying some things about what we know about it. See if this is on. Okay. Well, so I work in an area, maybe this one works. There we go. So I work in an area called algebraic complexity theory, and this is really a sub-area of computational complexity in the sense that we're interested in understanding the fundamental computational difficulty of various problems. And the algebraic part of this is that I want to measure difficulty or computational cost with respect to basic arithmetic operations. So the kinds of problems we're going to be interested in, these are problems that have some kind of algebraic or arithmetic character to them, and we'll solve them by adding and multiplying numbers together. And every time I add a number with another or multiply two numbers, that's one unit cost. And I want to measure the cost of my algorithms with respect to this. Now this area touches on a variety of topics within theoretical computer science. Most relevant to the program here, we already saw in JM's talk this morning that understanding the complexity of matrix multiplication and linear algebra more broadly. This is an extremely interesting area to study, and it sits really within this sub-area of algebraic complexity. This area also has its own version of the P versus NP problem. So if you've heard of this permanent versus determinant problem, this is some algebraic version of P versus NP. It's not so important you know what it is, but it is a genuine analog of P versus NP, and understanding this problem is it's a formal prerequisite to understanding the classic P versus NP problem. This area is also related to problems coming from symbolic computation with polynomials, which is a very classic topic, and this is the sort of thing that I want to tell you about today in this talk. And I just want to mention this is by no means an exhaustive list of what algebraic complexity people are interested in general. This is just to give you a flavor for what this area is about. So I want to tell you about a problem, and hopefully this is one that, depending on where you grew up and what educational system you were brought up in, maybe you heard about this in undergraduate, maybe it was kindergarten, but we're all kind of familiar with it. We have two polynomials, say f and g. And for me, let's just think of them as having rational numbers as coefficients. And we're interested in computing their greatest common divisor, the highest degree polynomial that simultaneously divides f and g. And the question that I want to tell you the story of in this talk is, what's the complexity of doing this? What's the cost of computing the GCD? Now, if you dig up maybe some good memories, maybe some bad memories, the Euclidean algorithm solves this problem. It gives you a polynomial time algorithm to compute the GCD, and if you implement it using fast polynomial arithmetic, using the fast Fourier transform, you actually get about n squared operations to compute the GCD. Here, n is the degree of these two polynomials, f and g. Now that's great, but we can do better. There's an algorithm that comes out of work by Knuth, Schoenhage, and Monk from the 1970s that computes the GCD in near linear time. It uses about n times log squared n arithmetic operations. So it's a near linear time algorithm, and it's actually a very beautiful algorithm. It's based on a divide and conquer approach. It's really, if you've never seen this, it's quite a beautiful algorithm. Although famously, it's a hard thing to implement. It took, I think, several years before any paper had a fully correct implementation of this algorithm. And there's actually a lower bound here. There's a paper by Volker Strassen, the same Strassen of matrix multiplication, that shows you need at least n log n operations. And under a more refined measure of complexity, if you just count the number of multiplications you perform, not additions, just multiplications, this lower bound actually matches the complexity of this algorithm. So with respect to time complexity, we fully understand how expensive the GCD is, but for me, I want more. Because in complexity, we often are interested in how do different problems relate to one another, when can we reduce problems from one problem to another, and this is something I want to understand. And to do this, it's often useful to organize our problems into complexity classes. So you've probably seen diagrams like this where we start with P, problems we can solve in polynomial time. And then sitting around this is NP, problems where we can check solutions efficiently in polynomial time. And then you can draw even bigger classes, problems you could solve in polynomial space, exponential time, and so on. But the GCD, this is a problem that we can solve in polynomial time. So we need to zoom in on this picture and look at interesting complexity classes sitting inside polynomial time. Now, I'm not going to have enough time to justify this choice, but believe me that one good measure of complexity within polynomial time is the amount of time you need to solve a problem in parallel. Not every problem seems parallelizable. Some are, and those seem simpler. So sitting inside here, there's a very small complexity class. Its name is NC1, but we don't need to worry about that so much. These are problems you could solve in log n parallel time. So if n is the size of your input, you need about log n time on a parallel machine, say with polynomially many processors.
I understand you have to read the input, so how do you...
Right, so it takes about log n parallel time to read the input, because if you imagine your algorithm as some binary tree of operations, and I have n inputs to read, it takes me log n depth to get to a point where I can read them all. Yeah, so this is kind of the minimum amount of parallel time you could spend. Sitting around this is an even bigger, well, we think a bigger class, NC2, where you might spend log squared parallel time, and you could keep drawing this diagram. There's a whole hierarchy of classes. We suspect these are all different, but like everything in complexity, we actually have no idea. So parallel time turns out to be a good measure of complexity within P. So let's get back to the GCD. What do we know about its complexity? So this is also surprising if you've never seen it. You can actually compute the GCD of polynomials in parallel by a reduction to linear algebra. It turns out computing the GCD is really about solving particular structured systems of linear equations. And essentially all of linear algebra you can do efficiently in parallel. It takes about log squared n parallel steps to compute the GCD. And in fact, this log squared n parallel time, this is conjectured to kind of be the right answer for parallel linear algebra. If you want an example, think about taking the trace of the nth power of an n by n matrix. The natural algorithm you'll write down for this uses about log n squared parallel steps, and we don't really know how to do better. So for the GCD, can we do better? And this is really some question about how does the complexity of the GCD compare to, say, questions in basic linear algebra, like inverting matrices and solving linear systems? And so far, this talk has been deep in the 1970s and 80s, and now we jump to the 21st century, and we can actually do better. So in work with Avi Wigderson just last year, we actually found a faster parallel algorithm for the GCD that uses log n parallel steps instead of log squared. And what I thought was nice about this is a different approach to parallelizing this problem. Instead of using linear algebra, we used some very nice identities from the theory of symmetric polynomials. I have no time to tell you about this, but I'd be very happy to talk to you during the break and tell you more. So this is one sort of problem that I like to think about. But it turns out the story is not done here, because we could ask for more. So there's one more problem that I want to tell you about, which is something called the Euclidean remainder sequence. So let's think back to what the Euclidean algorithm does. How do we compute a GCD? Well, we start with our two polynomials, f and g. We divide f by g. We get some quotient q1 and a remainder r1. And we keep going. We divide g by the first remainder, r1. We get a quotient q2, a remainder r2. And we keep going. Divide r1 by r2, you get a remainder r3. Keep going. Divide r2 by r3, you get a remainder r4. And this continues. Eventually, all the remainders are just 0, and then you stop. So I want to collect all of these remainders as a single object and call this the Euclidean remainder sequence of the two polynomials f and g that we started with. Now, why would you be interested in computing this sort of thing? Well, it turns out that this actually solves a lot of other problems in computational algebra. For example, if you have a polynomial and you want to understand how many real roots does my polynomial have in some interval, you want to compute something that looks like the Euclidean remainder sequence. If you have a power series that you want to approximate as a rational function, you want to do something like this. So there's a natural question here. What's the complexity of computing the Euclidean remainder sequence? And of course, we can do some kind of reduction to linear algebra. We get a log n squared parallel time algorithm. And the question here is, can we do better? And what I find really amazing about this is this question's open. We actually have no idea if you can do better than this log squared n, or if you could maybe get a log n parallel time algorithm. So I think this is one of my favorite questions in this area. I feel very stuck on it. But that's life. So that's all I wanted to say. Thanks so much for your time.
Thanks, Robert. Yes.
So is the bit complexity of your new log n algorithm different from the bit complexity of the original Euclidean? I'm just wondering, do you get larger numbers that you have to deal with in the middle of the algorithm, I guess?
So this is not something we explicitly thought about, but we don't get large numbers in the middle of the algorithm. The bit complexity would be, I guess, you'll never work with numbers that are maybe, not more than, say, polynomially larger than whatever you started with.
Yeah, so this
Strasson's lower bound, the n log n you mentioned, is
Yeah.
that just for multiplications, or is the input length n log n because the numbers are log n bits?
So the input length is 2n because you have the n, or maybe 2 times n plus 1. You have the coefficients of f and g's. The input size is n. It's on the number of multiplications you need. I lied a little bit. It's not for the GCD. It's for computing the whole sequence of quotients that you get from the Euclidean algorithm. That's really what the lower bound is for. But it is an n log n lower bound in the arithmetic circuit model.
What are the identities you can't tell us about?
So are you familiar with the Newton-Girard identities? Yes, so these are the sort of basic building block. For those who don't know, there are these two families of symmetric polynomials, the elementary symmetric and power sum polynomials. You can convert between these using something called the Newton-Girard identities. So we use those and a few very, in hindsight, simple tricks to compute things like resultants and sort of mess around with the roots of polynomials while you only have access to the coefficients.
Slightly unrelated, but are there either sequential or parallel algorithms whose complexity depends on the number of terms in the two polynomials and not on the degree? Because they might be sparse. So one or both might be sparse.
Right. I don't know, but I think that's a great question, and I imagine there might be work on it, but off the top of my head, I don't know.
Okay, well, let's thank Robert again. Unfortunately, our last speaker couldn't make it, so that actually ends this afternoon of lightning, maybe the slowest lightning talks you've ever seen. And now we have an extended coffee break, and we meet again at 3:45.